Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, Department of Mathematics. Today, I'd like to continue my discussion in third module. The topic is the expected utility principle. We are in the discussion of decision theory, which is a part of third module, and now we are extending our discussion with the concept expected utility principle. Let us look into the details. See, first, the heading is thoughts about utility theory in artificial intelligence. That means, this subject, the probabilistic modeling and reasoning, is exclusively designed for the branch artificial intelligence and machine learning. So now the concept utility principle, how it is related to the artificial intelligence. Utility functions are one of the elements of artificial intelligence solutions that are frequently mentioned but seldom discussed in details in artificial intelligence articles. Here, I'm trying to give you a small, brief, nutshell thought over role of utility functions in artificial intelligence. See, these are the elements which are frequently used in artificial intelligence, techniques, but we seldom address. That means we rarely address or discuss them, but we frequently use them. So that much importance the utility functions have in artificial intelligence. Let us look into what is utility function. Utility function are a product of utility theory, which is one of the disciplines that helps to address the challenges of building knowledge under uncertainty. See, the uncertainty plays an important role in analyzing the data sets. That means, the data science or artificial intelligence or machine learning, whatever you take, to extract the data from a huge database and analyzing the data set and recognizing the patterns. See, all this involves uncertainty. That means there may be a feature missing. How to fix that feature and how to get proper information from the available data. So this is a challenge. That is why here you use the knowledge challenges building under uncertainty. That means under uncertainty we have to face the challenge to complete the information where the labs are existing, and we have to make it proper. For this, the utility functions helps us a lot. See, utility theory is often combined with probabilistic theory to create what we know as decision theory agents. That means, by combining probability theory with the utility theory, we can make strong decisions or accurate decisions under uncertainty. Suppose there is a data set and there are missing features, and we have to predict what the feature that is missing, or we have to fill the data with labs in the data set. So for that, we will use probability theory along with utility theory to produce a better results and better predictions. Conceptually, a decision theoretic agent is an artificial intelligence program that can make rational decisions based on what it believes and what it wants. Sounds rational, right? That means a decision theory is nothing but an artificial intelligence program to make rational decisions based on what it believes and what it wants. So, given the data set and analyzing the given data set under probabilistic conditions, you have to make a rational decision basing on what you believe and what you want. What is the output you want and what you are observing in the input. Basing on that, you have to make a rational decision. So to make a rational decision, you must need a mathematical approach, and that mathematical approach is based on the probability theory as well as the utility theory. Now, in many AI scenarios, agents don't have the luxury of operating in an environment which they know the final outcome of every possible state. That means, see, whenever you are trying to deal with the artificial intelligence scenarios, that means whenever you want to interconnect uh, the machines to the computers and programs. Okay, that means whenever you're trying to deal with the artificial intelligence, see in the environment, the final outcome of every you may not know what is the final outcome exactly, what is going to happen exactly, what would be the output exactly. So if there exists always an uncertainty of the final outcome. Those agents operate under a certain degree of uncertainty and need to rely on probabilities to quantify the outcome of possible states. So when you are uncertain about the final output, you must rely on probabilistic methods. Okay, and that probabilistic function is what we call utility function. So you will use a function to map your input data set to some numbers, and basing on those numbers you will do some quantifications or calculations, and basing on those calculations you come to a conclusion. That's what you call, this function is called utility function. That means this utility function takes the help of probability and it maps the features or the data points to certain numbers, maybe 0 to 1 or maybe decimals or something, and by using those outcome by the mapping, that means the images of the mapping, we will use the calculations, and by basing on the calculations we will conclude. That is what utility functions. Okay, now probability theory is a tool for dealing with the degrees of belief about world states, actions, effects, etc. See, first of all, let us ask ourselves a question: what is a probability? What is probability? Probability theory is nothing about beliefs, predictions about a thing to be happened, that is a state or an action. What would be the state or tomorrow of certain thing, or what would be the action that a person is going to take the next day. So probability theory is a tool for dealing with the degrees of belief. To what degree you are believing about happening of something, whether you are believing to 90% extent or 80% extent or 60% or 35%. So what is your degree of belief? And the calculations revolving around those beliefs expressed in terms of percentages called probability theory. Now we explore utility theory to represent and reason with preferences. Yeah. So here, now let us come to the utility theory. Utility theory to represent and reason with preferences. Here, not only like in probability theory, we don't not only dealing with percentages. Apart from that, we'll take preferences, which would be preferable, which action or which strategy would be preferable, or which outcome should be preferable. Like that, we'll make some preferential order. Okay, basing on the probabilities. Basing on the probabilities, suppose this event has this much of probability and this event has this much of probability. So basing on the probabilities, we'll arrange the events in an ascending order or descending order, and that order plays a vital role in utility theory. So preferential order basing on the probabilities is the root cause for utility theory. Okay, now the agent's preferences are captured by utility function. Now after writing the events in an ascending order, descending order, or in a preference order, basing on the probabilities, list out the events in order, in a preferential order. So I prefer this as first, I prefer A as first, I prefer B as second, I prefer C as third, I prefer D as, like that. Then you will use a function f to map these preferences to some numbers, and this function is called utility function. So utility function is nothing but mapping the preferences to some real numbers is called utility. Now, which assigns a single number to express desirability of the state, and the number which you have mapped tells you the desirability of the state. That means how strong that event is desired to be happened, how strong, how intense that you are related to that event to be happened. Okay, that is expressed by that number. So that function helps you to disclose the degree of intensity or the degree of what you call desirability of the event or state. The expected utility of an action given the evidence is just the average value of outcomes weighted by their probabilities. Here we are being introduced with one more important virtue of utility theory or point of utility theory. Let me write it. Let me explain it. See here, we are now we have defined utility function. Okay, what do you mean by utility function? It's just nothing but a mapping from what? From the set of preferences, a, b, c, d, so on, to the set of real numbers, or you can call 0 to 1. Okay, the numbers between 0 to 1, you will map them, or some numbers, right? This is called utility function. How you have uh, made this order like preferential order basing on the probability. That means p of a, p of b basing on some probabilities. You have designed this order and you have mapped all those events to some numbers. Okay, now you are defining expected utility. What you call expected utility? What is expected utility? Okay, let me explain this. Expected utility is nothing but expected utility given evidence. Evidence means say this is going to happen for sure. If you assume that this will happen for sure, then what is the probability that, or what is the expectation that you will occur? Okay, you will occur. That means assuming that is occurred already. Assuming that is occurred already, what is the expectation about happening of you? That is called expectation of you given e. So, basing on the given evidence, what is the expectation of utility function? Function u, okay, is defined as sum of all probabilities of happening of what you call the results a multiplied by the values of u of s, the weights. That means you have a utility function u defined on your preferential set to the real numbers. Okay, let us suppose this is s, then the elements is s1, s2, then this is s1. Okay, and this runs from say what you call s1, s2, so on. The summation runs on s1, s2, so on, and this is nothing but probability of happening of s1 given e or given e. Okay, let me write it more clearly. So the utility function is nothing but, first let us define a utility function on a set of preferences, say s1, s2, s3, so on, sn. This is called the domain s, and they are mapped to some numbers. Let us call them u of s1, u of s2, so on, u of sn. Now expected utility of happening of u of a given e is already happened, and given that evidence e, what is the expectation of event small a is happened? It is defined as sum of all probabilities that si given e multiplied by u of si running over si. So say this is sk. So this is what you call expectation of utility function. And a rational agent should choose that action that maximizes the agent's expected utility MEU. That means you will calculate for each k. For each k, you will calculate E of uk given E, and among them you have to choose the maximum of all. That is called the corresponding action k, the kth event action, or the sk strategy. Sk is called the correct strategy, or what you call maximized expected utility strategy. Okay, so when you summarize these things, you'll come to understand that uh, after calculating for each k, you will calculate u of sk given the evidence E, and this is you will calculate for each and every k is running from 1 to n. Okay, then you will choose the maximum of all this expectation of u of sk's. Okay, that tells you the which strategy will work more efficient, or which strategy will be more appropriate in that particular uncertain situation. So that is called maximizing expected utility principle. Okay, that means do the right thing. Simple. The maximum, you choose the maximum benefit you will get, the maximum profit you will get. That's what do the right thing. Do the right thing means choose the highest utility. That means you will choose the maximum of all the expectations. That's what it means. Now, frequently it is easier for an agent to express preferences between states. See, suppose there are two states, A and B. States means the choices ahead of you to make a decision A or decision B. Or, okay, when you have a data set and you have a missing feature, whether it would be A or B, that is the decision you have to make, whether the missing column would be A or B. So, whenever you have two preferences, A and B, okay, then you may make that A is more preferable than B, that is expressed as A greater than B, and you may say that A is less preferable than B, that is called as A less than B, and you may prefer that both are equivalent, and either of the things will work. That means A is as equal as B. Okay, that means indifferent. A and B are indifferent. That means you can find no even single inch of significant difference between A and B. So you can prefer any of the things. Both of the things will work equally. That's what. So there are three kinds of preferences. That is, A is preferable to B, that is A greater than B. B is preferable to A, that is A less than B. Or A and B are equally preferable. Now, what sort of things are A and B? What sort of things are A and B? They could be states of the world, but more often not there is uncertainty about what is really being offered. See, what are the first, now here we are discussing about the point, what do you mean by states? What do you mean by state A, state B, state C? That's what here are preferences A, preference B, preference C. They are nothing but states of the world, okay, under uncertainty. But what really is being offered? That means under uncertainty, under random situations or probabilistic situations, you will have some choices A, B, C, and you have to pick one of these A, B, C as your final decision. So these choices are termed as states. That's what they are termed. States are nothing but the choices ahead of us or in front of us under uncertainty. Okay, we can think of the set of outcomes of each action as a lottery, say with S1, S2, Sn with the probabilities P1, P2, Pn. That means suppose we are playing a game, kind of lottery game. That means we are betting on some numbers S1, S2, so on, Sn. And the probability of getting S1 or winning S1 is P1, and probability of happening of S2 is P2, so on, probability of happening Sn is P1. So when you have this, then each S1 is termed as a preference. That means a state. S1 is the first state, state 1, state 2, state 3, so on, n states. That means n choices you have, and you have list of probabilities. Basing on this list of probabilities, you will arrange these states in a preferential order. Suppose S3 has highest probability, so you will prefer S3 as first. Next, S7 has highest probability, then you will write S7, like that you will arrange. That's what he's telling. Example of lottery, food in airplanes, chicken or pasta. You may expect when you are just boarding into an airplane, you may have today, what would be the lunch they are going to offer, whether it's a chicken burger or pasta. Okay, so you have due to your previous traveling experience in that airplanes, in that airlines, you have this 88 out of 10 times, 8 times you have taken juicy chicken, and out of 10 times, 2 times you have taken overcooked chicken, and 77 times you have delicious pasta. Out of 10 times you have congealed pasta. That means whenever you are offered in that airplane, whenever you are frequent, suppose you are frequently traveling that in that airplane, and whenever you traveling that airplane, out of 10 times, 8 times they used to provide a very tasty, delicious chicken, but 2 times they will used to provide not a delicious, that means little overcooked or light. And out of 10 times, 7 times they used to provide delicious pasta, but 3 times they failed to provide delicious pasta or not tasty. Okay, that's what you have an idea. Now, see here, rational preferences should lead to maximizing the expected utility. If the agent violates them, it will exhibit patently irrational behavior in some situations. That means among the preferences, while choosing one of the preferences, you should be very rational. The agent, the person who is making decision to pick one of the preferences, he should be very rational. He should not be biased. He should not be influenced. He should be rational. That means very practical. That's what it means. We require several constraints, or what you call axioms of utility theory, that rational preference should obey. That means, suppose you have made a decision when you have a set of preferences and you have to make a choice, or you have to pick one preference among that. Okay, and the preference or the choice you made is said to be a rational preference or rational choice only if it satisfies the following conditions, that is called axioms of utility. Number one, orderability. That means the choice you have made, suppose you have picked up A, you should be able to, whenever the other choices are given, you should be able to tell which is preferable, and that means whether A greater than B or A less than B or A equal. You should be precisely able to tell. If you are not able to judge, that means you have not made a good decision. That's what it tells. And transitivity, that means if you have made two choices, say A comma B, and you are given third choice C, and you must be able to compare whether, and if you know that A is less preferable than B and B is less preferable than C, then automatically A should be less preferable than C. If it doesn't satisfy, then your preferences are not at all called as rational. That means if you make two preferences, two choices, A and B, and whenever you are assigned with C for comparison, then you found that A less than B, that is A is less preferable than B and B is less preferable than C, and if you are not able to tell that A is less preferable than C, then your choice of A and B is not at all called rational choice. Okay, and continuity. That means whenever you have three preferences A, B, C, such that A is more preferable than B and B is more preferable than C, then there exists a number small p such that the probability of happening of A is P, and the probability of happening of not A, or either B or C. Not A means either B or C should be 1 minus P. That's what continuity. Okay. And substitutability. Substitutability means if you have two preferences A and B, and neither A greater than B or nor B greater than, that means A should be equivalent to B. That means if you replace with B also, it works. Okay, then it is called substitute. In that case also, your choices are called rational. That means if you are able to tell whether A is preferable B or P is preferable, then your choice is called rational. And transitivity, more than one choices, transitivity, then also your selection is rational. Continuity, then also your choice is rational. And substitutability, then also your choice is rational. And monotonicity. Monotonicity means whenever A greater than B, he's telling that whenever A is more preferred than B, that means probability of A should be greater than probability of B. That is called monotonicity. That's automatically. That means when you say that A is this strategy A works than B, that means the probability of A should be more than probability of B. There shouldn't be any ambiguity in that. And decomposability. That means P of A union B union C could be P of A plus P of B plus P of C. That means probably that means the preference of selecting A or B or C. These should be like their sum of individual preferences. That is P of A plus P of B plus P of C. Okay, this is called decomposability. If any of these axioms are satisfied, then your selection is said to be rational. Otherwise, your selection is not at all said to be rational. That's what you call axioms of utility. Okay, now the axioms of utility theory are axioms about preferences, but we can derive the following consequences from them. Okay, say here, that means existence of utility functions such that U of A is less than U of B implies A is less than B, or U of A is equals to U of B implies and implied B A is equivalent to B. That means a function is called utility function. That means you have a function f from the set of all preferences, that is what you call A, B, C, D or so on, and they are mapped to some real numbers. Okay, this is us. Then this function is called utility function if it satisfies the following two conditions. Number one, whenever the image, that is U of A and U of B, okay, whenever U of B is less than U of B, that means A must be less preferable than B. And whenever A is less preferable than B, automatically the number should be in this order. That means U of A should be less than U of B. Okay, if this doesn't imply this or this doesn't imply this, then that function is not at all called an utility function. Okay, similarly, whenever U of A is equal to U of B, then A must be an equivalent strategy of B. That's what the basic existence conditions of utility function. Now, expected utility of a lottery. That's what just in the previous slide I have already discussed with you. Okay. See, a utility function exists for any rational agent, but very unique. That means what he is selling is, suppose you have a utility function. So here we are going to see one important result, that a utility function exists for any rational agent but is not unique. That means when you have an utility function U of S, and whenever you multiply that with a constant A, and that is also a utility function, and you multiply with B, that is also a utility function, and whenever you add with that function with a constant K, that is also a utility function. So what, in summary, what you can tell as is the multiple of the utility function U of S with a number and added to a constant is again a utility function. That's what this the second rule says, that it need not be unique. That means there, once you get a utility function, you can build so many utility functions by adding a constant or by multiplying with a constant. That's what. Existence of utility function does not necessarily mean that the agent is explicitly maximizing the utility function. By observing its preferences, an observer can construct the utility function. That means just merely building an utility function is not sufficient to make a decision. After building an utility function, you must observe the preferences carefully, and basing on the practical thinking, mixing the practical thinking with the outcomes of the utility function, then you can make a better choice. That's what he's saying. Okay, now Even though the decision theory and machine learning are very closely related, machine learning community traditionally focuses on the aspect of problem, either loss incurred from mistakes of distribution of data or simply the probabilistic representation. So yeah, the decision theory is very closely related to machine learning. There's no other doubt. But the thing is, how to minimize the loss while making the decision. That means basing on under uncertainty, you'll use probability theory and utility theory, and you'll make a decision. While making decision, there might be a loss of information. How to minimize that loss? That is a challenge again. That is one more challenge. So minimizing the loss while making the decision under uncertainty is also one important thing that we have to focus. And now, the information for a decision is often summarized in a payoff table. Then we can apply this method that is called payoff methods. Payoff methods helps you to minimize the loss of information while making decisions. This is also a part of utility theory. That means you will construct a payoff table. That means you will assign a number, either profit or loss, or benefit or gain or lose, what you are going to have occur, face by making that decision. You will list out it in a table form. That is called payoff table. Payoff table is nothing but a table which represents the numbers representing either gain or loss due to the decision you are going to make or the choice you are going to make. Okay, right. Now, suppose here I am going to show you a small example. So, suppose you are going to install, you want to install a big printing machine in your shop, in your stationery shop. So whether you have to go with a small Xerox and printing machine or a medium capacity printing Xerox machine or a large capacity printing or Xerox machine. Small means at a time it will give 20 pages with a single instruction. Medium means it can print 100 pages and large means it can print 1000 pages. So capacity of the machine that defines whether a small facility or medium facility or large facility. So whenever you choose small facility, see the profit you are going to occur is $10 per day. With a moderate facility, the demand for small facilities $10 and moderate facilities $10 and high facilities also $10. That means there are three states: low demand, moderate demand, high demand. You have three choices, three preferences, that is small facility, medium facility, large facility. Whether to install small Xerox machine or a medium Xerox machine or a big Xerox machine. And the three states have, on a particular day you may have low demand for photostat copies or a moderate demand or high demand. So when you have low demand with a small facility, you will have $10 of profit. And moderate demand also you will have $10 profit with small facility. On a high demand day also you will have $10 of profit. But with a medium facility, you will have $7 of profit with medium facility, and on moderate demand you will have $12 with medium facility, and when high demand again you are going to have $12 of profit. But with a large facility, that means large machine installed, you will have minus $4. That means you may lose $4 when there is a low demand for Xerox, and $2 of profit when there is moderate demand. But when you have a high demand, that is $16. Say suppose you are running your Xerox or printing shop or nearby a school. Suppose the school is a holiday, then you will have low demand. Suppose the school is a working day, normal working day, then you will have moderate demand. Suppose the school is going to have exams in a week, then you will have high demand for Xerox. That's obvious. So students, when there are no students, that means holiday, you will have no demand, almost low demand. And when normal days of schooling, you will have moderate demand. But during examination days, so many students will rush to your shop for Xerox, that is why you will have high demand. So there are three states of future, that is low demand, moderate demand, high demand, and you have three choices whether to buy small machine or moderate machine or big machine. So which would be the wisest decision? Okay, this is called payoff table. This because this represents the profit or loss in terms of numbers. Profit is denoted by positive and loss is denoted by negative. So that is why this is called a payoff table. Right. Now, so here thing is decision making under certain or uncertainty. Actually, you have to tell uncertainty, not certainty. The alternatives you have small, facility, medium, and loss, and the future states are low, moderate, high. What will you choose to build if the demand will be low, moderate, and high? Under low state, which facility is preferred, and under moderate demand state, which facility is preferable, and high demand state, which will do? These kinds of questions you will have. Okay. He's telling that if the demand will be low, just choose small facility with a payoff 10 million. That means if you believe that in that area you will always have a low demand, you better go with small facility because you will have 10 millions of profit on an average. But if the demand is more moderate, better you choose medium facility because $12 million of profit you can have. And when you believe that there will be high demand always, all the days, all 365 days, then you can go for this. But this is not certain. You cannot tell that all the days you will have high demand or all the days you will have moderate or low demand. So that is the question. That is the challenge really we have. So here we are using one approach to make decision under uncertainty, that is called max-min approach. Max-min approach. See here, what we are doing under max-min approach, we will choose from corresponding to each alternative, we will choose the least amount of the corresponding row. That is, what is the minimum of these three numbers? 10, 10, 10, that is 10. What is the minimum of these three numbers? That is 7. What is the minimum of these three numbers? Minus 4 plus 2 plus, that is minus 4. So what you have? 10, 7, minus 4. So what you have done, you have chosen the minimum and the next minimum and the next minimum. Now among these three, if you choose the maximum, that is 10. What is the maximum of these three? That is 10. So the corresponding facility, that is small facility corresponding to low demand, is the wisest decision under max-min approach. In order to maximize your profit under minimum expected demand, under minimum very lowest demand, in order to maximize the profit, you better go for small facility. That's what it is stated. So this is a kind of approach of making decision under uncertainty. That is called max-min approach. Okay. Now here we are going to another kind of criteria or approach called mini-max regret approach. Mini-max regret approach. Here, first we will choose choose the maximum of the column. That is, in this column, what is the maximum? That is 10. And in this column, what is the maximum? That is 12. And in this column, what is the maximum? That is 16. Now we will subtract that selected number from each and every entity. That is 10 minus 10, 0, 10 minus 7, 3, 10 minus of minus 4, 14, 10 minus 10, 12 minus 10, 2, 12 minus 12, 0, 12 minus 2, 10, 16 minus 10, that is 6, 16 minus 12, that is 4, 16 minus of 16, that is 0. Like that you have prepared. That means you have chosen the maximum of each column, maximum. Then you have subtracted, then you got a new payoff table, a new resultant payoff table. Now you are choosing the highest again, that is 6, and again the highest, that is 4, and again the highest, that is 14. Okay, that means you have subtracted the maximum number from each column, and after getting a new resultant table, again you are going for or you can tell that you are going for the maximum of each row, that is 6, 4 and 14, and among these you will choose the minimum, that is 4, and you will go for medium facility. This is called maximum. That means after choosing maximums, you are preferring the minimum. Okay, that means it is like minimizing the loss. The previous strategy about maximizing the profit, this is like defensive. Defensive means minimizing the loss. Okay, now uh, now let us look into the next concluding slides. I'm going to conclude the session with a few things. With that way, I would like to conclude. Machines learn by means of loss functions. It's a method of evaluating how well specific algorithm models the given data. If predictions deviates too much from actual results, loss functions would cough up a very large number. Gradually, with the help of some optimization function, the loss function learns to reduce the error in prediction. In this article, we'll go through several loss functions. That means it's a leading to the next lesson, which is, see, whenever we are making choices or decisions from the given preferences or given choices, there is always scope for loss of information. So in order to minimize the loss, we'll design loss functions. Okay, for that we'll use some algorithms. Okay, and so those algorithms or loss functions will help us to minimize the loss of information. This is what the intention of this, and I'd like to show you some loss functions here. The mean square error, the loss function called mean square error function. Here you will calculate the loss of a data set. Say you have a data set y1, y2, so on, yn. You have a data set y1, y2, so on, yn. Now, from this you will calculate y bar. You will calculate y bar. Okay. Now, what do you say? You will, after calculating the mean, you'll take the deviations, that is y1 minus y bar, y2 minus y bar, y3 minus y bar, so on, yn minus y bar, or yk minus y bar. You can tell k. And you will square everything. That means to make every quantity positive, you will square. And you will add all of these things. Okay, I is equal to 1 to k. And you divide with k. The resultant value will be assigned as the image of the corresponding strategy y. That means the m of y will be this number. So like that, for every strategy, every data feature y, say it y, this would be, and for the data set x, it would be m of x. For the data set z, it would be m of z. Like that, you will construct this function, and the function is called mean square error function. This also helps you to minimize the loss of the data while making decisions under uncertainty. So this has a very important role in designing algorithms for machine learning or artificial intelligence. Okay. In the same way, we have one more function called mean absolute error. Here, suppose you have a data set y1, y2, so on, yk. In the same way, you calculate y bar, just you have done in the previous, and you will calculate the deviations y1 minus y bar, y2 minus y bar, y3 minus y bar, so on, yk minus y bar. Now you will take the modulus of everything, modulus of everything, modulus of everything. These are called absolute errors. These are called absolute errors or deviations. Now you will add all of these things. You will add all of these things and divide it by n. you will get a number which is called mean absolute error, and you will assign that particular data set with that number, and the function which helps you to assign like that is called mean absolute error function. This also plays an important role in minimizing the loss of information while making decisions on transitivity. Okay, in the same way, you have some other functions. I'm just mentioning them. One important is hinge loss function or SVM loss function. Okay, uh, here you will calculate some deviations and add with one, and you will choose the maximum of 0 or this number, and you will add like that. It would be a kind of function is called sum of scores fall incorrect categories by some safety margin, maximum margin classification. Okay, it's called hinge loss function. It's also very important in very important loss function. These are all called loss functions. Say it is mean square error or mean absolute error or SVM loss function. All these are called loss functions. These play a very important role in designing algorithms, and these help us to minimize the loss of information. Okay, so here you could see how this has been executed with an example. That means a SVM loss function. Here you are observing two images. One is of a small dog and one is a cat. You have listed a data set and one more picture it's missing. It's about horse. Okay, you have written the numbers, say maybe pixels or somewhat. You have written the numbers, image related to the image might be pixels or the length or breadth or whatever you have listed in a table. Now here in the first training example, that means in the uh, image one, that means in the first image of certain quality, you have calculated this with the help of SVM function for this. Okay, and you have added, okay, you have calculated for this, and you have added all the three things, this you have calculated SVM losses for these three things, and you have taken the maximum with 0, and you got the answer as 8.48. So that means it is telling that you are going to lose high information, because 8.48 means high level. That means high loss you are going to occur in this when you choose this first training or first image. So better go for second way of imaging. In the second of image, the loss is 0. That means you could prefer this image processing method, the second method. That's what it is. Method 1, method 2 of processing of image. 3 images, dog, cat, horse. Here under first training, by using SVM method, you got 8.48. That means very huge loss of information. Here 0, that means no information. That means you have to prefer method 2. That's what it is. So with this, I'd like to conclude my lecture on expected utility principle and the payoff functions and the loss functions. And in the next class, we'll meet with one more interesting topic from the third module. Thank you for your patience listening. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.